It is July 5th. Good morning, I'm Miss Matos. I will be teaching you Earth Science today. We just finished talking about Wegener's theory of continental drift and how the face of the Earth has changed over time. We talked about Pangea. We've talked about all of the different shapes that the continents have formed over the course of Earth's history. So I want you to think back. Our do now for today is I want you to think back about what process causes continental drift. And I want you to draw me a very simple diagram or picture explaining that process. So go ahead and take a moment, and I want you to go ahead and draw that process. All right. If you could go ahead and take a picture of that and upload it in the chat so I can see what you have. They all look really great. So your picture should look something similar to this. All right, we talked about this convection current. Convection current is that process that is moving the big slabs of rock, those continents, around the Earth. All right, and in our convection current, as you can see right here, by the core, that magma heats up, and as it heats up, it rises to the top. And as it rises to the top and away from the heat source, it cools down and falls back down, creating that cyclical movement, that motion. So I want you to think back, what can we connect this idea of convection currents to? Where's another place that you've seen it? Yes, Jessica, thank you. A pot of boiling water, right? You all have seen this process happening in a pot of boiling water. Oh, even better, a lava lamp. Perfect. That lava at the bottom of the lamp, it heats up when it's near the light bulb, and as it comes to the top, it cools off and it drops back down. So we see that constant motion, right? We see so many different processes on Earth and in space, all throughout Earth and space science, really, that is powered by some form of convection. So I want you to keep that in the back of your minds as we start to talk about the movement of these tectonic plates. So as the continents are moving, the plates that form the Earth are also moving because of the same process, all right? By the end of today and over the course of this unit, we want to start to think about answers to our essential questions. So how do plate boundaries interact? And how do constructive, putting together, and destructive, taking something apart, natural processes on Earth change that the face of the Earth over time, just like what we experienced with our continental drift lesson. By the end of today, our objective is that you will be able to compare and contrast the three different types of convergent plate boundaries. So this is going to be the first type of plate boundary that we're going to look at. There are three different ones, and in this specific type, convergent plate boundaries, there are three types. All right, I need everybody to go ahead and get their science notebook ready. We're going to start with our vocabulary today. And then we're going to move into a video to look at how those plate boundaries work in a visual sense. And we're going to practice what we learned today. As you get ready to take notes on the new vocabulary, I want you to think about what this new vocabulary means, right? Big term today is going to be convergent. Convergent. Has anybody heard of a word similar or can think about what maybe that word means? Convergent. I love it. In the chat, someone referenced the movie Divergent. Divergent is going to be another one of the plate boundaries we discussed, and it's the exact opposite of convergent. So do you remember what divergent was about? Yes, we had people who were moving away from the norm, moving away from the center. So divergent is moving away. Convergent is going to be coming towards. So convergent, coming towards, divergent, moving away. Very, very good. So when we talk about our plate boundaries, there are going to be two specific types of plates that we're going to look at, and two types of the Earth's crust. We're going to have our continental crust, which is kind of like a big fluffy towel. All right, we've got the big fluffy Spider-Man towel here. This one's very thick. You can see it's very, very thick. Okay, our continental crust is mostly granite. It's very porous, very thick. The oceanic crust, on the other hand, is going to be our thin towel. You can see the size difference here. All right, we have the big thick towel versus the thin towel. Oceanic crust is much more dense, and that's because it has that pressure and the weight of the ocean bearing down on it, compressing that basalt. All right, so those types of crust determine the kind of convergent plate boundary that we're looking at. Each type is going to make a different landform, or it's going to have a different process that is associated with it. Let's go ahead and jump right in here. We've got our oceanic crust and our continental crust. Right, so as we discussed, our convergent plate boundary is going to be when two tectonic plates move towards each other. So that mantle is convecting underneath and it's pushing those plates closer together. Now the density or thickness of those plates, whether it's that oceanic or continental, is going to determine what will happen. So we have three types of possible collisions here. We have where continental crust can come into contact, and let me go ahead and get my towels here, with more continental crust, so two thick pieces together. We can have our oceanic crust coming into contact with another thin piece of oceanic crust, or we can have a boundary that combines both our continental and oceanic. All right. I want you to think about where else you've seen something colliding together. What's another time you've seen in your world? Let's bring it to your world. If you said a car accident, you were correct. So this is essentially what happens with tectonic plates. The force that you see with our car accident, you're going to see the same type of force because we have massive pieces of rock moving towards each other. And even though they're moving very, very slowly, there is enough force because of the density and the mass of the rock to create a lot of damage and to make something new from that damage. All right, so let's look at our types of convergent boundaries. I just want to make sure we're doing okay on time here. All right, our continental. This is where, and I think it's pretty self-explanatory, but we have plates that are the same density and they're going to be the thick, fluffy towels, okay? Neither of them are going to sink because they're both very large. And so when they push into each other, they're going to move in an upwards direction, okay? So you can see on the screen here where we have two large pieces of continental crust pushing into one another. And as they do, they will go up. And this is what will form our mountain ranges. We see this in North America all over the place. Our Rocky Mountains, the Olympic Mountain Range, Mount Rainier, we have the Appalachian Mountains. All of these different mountain ranges are those convergent plate boundaries that are pushing upwards. They're the landlocked continental plates. We see it in Europe with the Alps, the Himalayas. All right, so all of those mountain ranges are because of those continental plates that are pushing forward. So in your notebook right now, you should have your continental, and that they form mountain ranges and high plateaus. give you a moment just to catch up on that. And then we're going to talk about oceanic and oceanic. Okay. So our oceanic and oceanic, obviously both of those are under the ocean. They're going to both be compressed really, really thin. Okay. Get two very thin pieces because they're very dense. The weight of the ocean's pushing down on it, it's compressing it. The older piece, the one that's going to be more dense or thinner, is going to be pushed under our younger, less dense piece of oceanic crust. So right here, if you follow, okay, we have the more dense piece being pushed down by the younger, less dense piece. As it gets pushed down, it creates what's called a subduction zone, right? Subduction. And when it creates that subduction zone, it goes down, it's pushing towards the mantle. And we know what happens when rock is towards a heat source, like in the mantle, it's going to melt. And this is what creates our underwater volcanoes. All right, it creates an ocean trench. The trench there, because there's a big, deep area where the two plates meet, almost forms a V, all right? And in the little spaces in between those two plates, where the one is going down and the other one's pushing this way, we have magma, that melted rock coming up, forming underwater volcanoes. So that is oceanic, oceanic, right? Everybody take a moment and get that in your notes. And then we're going to get into the really fun one, is when we have a piece of continental crust that collides with oceanic crust. So we have our oceanic and continental. All right. So as you can see in our diagram right here, we have our continental crust as our big, thick towel. And here it's meeting that oceanic crust, which is really, really thin. All right. So the continental crust acts almost like a big bully, and it pushes the oceanic crust down. Okay, just like this. And it creates that V again. And just like in the oceanic, when it creates that V, that downward cycle, okay, we have a new trench formed, and we also get our volcanoes on land. So those spaces in between are where the magma can rise up and form our on-land volcanoes. So very similar to oceanic, except with oceanic, it's underwater volcanoes. And with oceanic continental, it's going to be our above ocean on land volcanoes. All right. So before we move any further, I want to show you a small video clip on how this works. All right, let's go ahead and watch this, because everything is not moving at the same pace all the time, right? We have that mantle that's constantly flowing, and it's pulling those plates along with it. And so this is how it's going to look.
We are a place where creative dreamers go to learn their craft.
There we go.
The idea that our planet's continents drift around the globe, periodically glomming together and breaking apart, is at least 200 years old. But most geologists didn't believe it until the 1960s, when mounting evidence made it clear that the Earth's crust is broken up into fragments, and that those fragments, called tectonic plates, are moving. And these days we directly track that motion, with millimeter precision, from space. The common simplified explanation for why tectonic plates are moving is that they're carried along on currents in the upper mantle, the slowly flowing layer of rock just below Earth's crust. Converging currents drive plates into each other, diverging currents pull them apart. This is mostly true. Hot mantle rock rises from the core and moves along under the crust until it grows cool and heavy and sinks back down again. But the plates aren't just passively riding these currents around like a bunch of suitcases at the baggage claim. They can't be, because some of the plates are moving faster than the currents underneath them. For example, the Nazca Plate, a chunk of ocean crust off the west coast of South America, is cruising eastward at about 10 centimeters per year, while the mantle underneath it oozes along at just 5.
All right, so here's an example of our oceanic crust. See how much thinner that is and how much more dense it is than our continental crust right here. This is where that Nazca Plate bumps up to South America, all right? So it is moving faster than the mantle underneath, and we're going to see why that happens and what is the mechanism that pulls that plate downward into the mantle.
Neither tectonic plates nor luggage can move faster than the belts they're riding on unless something else is helping to push or pull them along. And some of Earth's plates, it turns out, are pulling themselves. When an ocean plate collides with another ocean plate, or a plate bearing the thick crust of continental land masses, the thinner of the two plates bends and slides under the other. As the edge of the sea floor sinks into the mantle, it pulls on the plate behind it, the same way a chain dangling further and further off a table will eventually start to.
Okay, so this is how that downward motion happens. Just like if you were to have a chain right here, all right, coming down off the side of your desk, how it starts to move very quickly. It gets pulled and it's pulling that piece of plate down with it. This is going to make that plate move much faster than the convecting magma underneath.
Slide. The bigger the sunken portion of the plate becomes, the harder it pulls and the faster the remaining plate behind it moves. You can find where this is happening just by looking at Google Earth. The incredibly deep, narrow ocean trenches visible off the coasts of some continents and island chains mark the creases formed as ocean crust plunges downward, bending the edge of its neighbor in the process. What's more, these chunks of seafloor are actually helping to drive convection in the mantle beneath them. Sunken slabs of ocean crust block flowing rock from moving further sideways, forcing it to turn downwards and sink. And eventually those slabs get too heavy and break off, plunging slowly toward the core and creating a suction force that pulls mantle material along behind them. So in some ways, seafloor crust is really more like part of the conveyor belt than something riding on top of it. The continents, on the other hand, are baggage.
Okay, so let's practice what we've talked about today. All right, we have our continental crust, our oceanic crust, our convergent coming together plate boundaries, and our subduction zones, where that one piece of oceanic crust is pulled down and the continental crust, or the other less dense piece of oceanic crust, is still moving to the side. Let's go ahead and take a look at that. All right, so using our new vocabulary in the chat, I want you to fill in the blanks for the numbers that do not have the blanks filled in just yet. And we're only going to use our new vocabulary words from today. So continental crust, oceanic crust, subduction, and convergent. We only have 4 terms that we're going to use today. I've already labeled for you. Number 1 is our volcanoes that are formed. So let's think about what type of plate boundary is going to form a volcano. Number 3 is that magma. It's that molten rock in the mantle. Number 5 is the ocean pushing down on that new piece of crust right there. And number 8 is the mantle. So let's look at number 2, all right? Number 2, that crust is above the water. Some of it's below, but most of it's above the water here. What type of crust is number 2? Yes, yes, very good. That is our continental crust. So go ahead and type continental crust in for number 2. And this is all going into your science notebook. So number 2 is continental crust. Very good. Now let's look at number 4. All right, what do we have happening here? What is going on? What process is happening in this particular spot? Yes, we have that V forming, right? And when the V is forming, what is going on with the crust there? It's being pulled down. And what is our new term for being pulled down? Yes, that is a subduction zone. So that is subduction. Very good. Okay, now let's look over here at number 6. So at that subduction zone, what type of crust is being pulled down? Exactly. It has ocean sitting on top of it, making very tightly, densely packed crust. So that is going to be our oceanic crust. And number 7, we want to look at those arrows. Okay, those arrows are pointing towards each other. What type of plate boundary is moving towards each other? Very good. A convergent plate boundary. All right, I'm going to leave this up on the screen for just a moment, and I want you to make sure to have this in your notebook. You guys are doing a great job today. All right, so to end out today, we are going to do an exit ticket. An exit ticket ask you. And I want you to answer this in the chat. So everybody go ahead and give me your best answer. What is formed at a continental oceanic subduction zone? Is it A, an ocean trench, B, volcanoes on land, C, seafloor volcanoes, D, which is both an ocean trench and volcanoes on land, E, both volcanoes on land and seafloor volcanoes, or none of the above? I'm going to wait until everybody puts their answers in the chat. Where we're at. If you have to go back and look at your notes, go right ahead. Great job, guys. It is going to be D, both an ocean trench and volcanoes on land. And your hint here is that there's continental crust involved. When there's continental, we will have something that's formed on land. You guys did a great job today. If you have any questions, please feel free to reach out and message me on our learning management system through the chat. And I look forward to seeing you guys again next time, and we will talk about divergent plate boundaries next. Have a wonderful day.